Hello everyone, we are the group number 1 and today we are going to discuss about the characteristics of solenoids and toroid. So first of all, what is solenoid? A solenoid can be defined as a looping conducting wire. It has as many loops as required to produce a stable magnetic field. The magnetic field direction produced by a solenoid is straight inside of it. It has no component except its horizontal. Additionally, it is mostly made of electromagnets, which are widely used for industrial purposes. It is also more flexible than a permanent magnet. As you can see in this slide, there is a figure, and that is the structure of a solenoid.
Let us now discuss the types of solenoid. There are different types of solenoid. First is the AC laminated solenoid. It is a type of solenoid that operates with alternating current. It has a laminated core made up of thin layers of iron or steel sheets that helps to reduce energy losses caused by eddy currents, making the solenoid more efficient. These solenoids are commonly used in applications such as HVAC systems, appliances, and industrial machinery. Second is the DC C-frame solenoid. It is a direct current solenoid that has a C-shaped frame that holds the coil and provides support. These solenoids are typically used in applications where a compact and reliable solenoid is required, such as automotive systems, vending machines, and electronic locks. And then there is the DC D-frame solenoid. It is similar to DC C-frame solenoid. It is a DC solenoid but with a D-shaped frame that provides additional stability and support to the solenoid. These solenoids are commonly found in applications like door locks, medical devices, and industrial equipment.
On the other hand, a linear solenoid, according to its appearance, has a shorter diameter and longer axial length. This is a type of solenoid that produces a straight line mechanical motion. This generates magnetic field whenever an electric current flows through the coil of the wire. So there is a plunger or a movable iron rod inside the coil and is being pulled or pushed by the magnetic field in a straight line. This straight line motion is used to push, pull, lock, and release such mechanical components. This type of solenoid was also used in various applications such as door locks, electric valves, and other automotive starter motors. While for the rotary solenoid, according to its appearance, it has a bigger diameter and shorter axial length. This converts electrical energy into a rotational motion. Unlike linear solenoid, the magnetic field causes the rotor to twist or rotate, which generates angular displacement. This type of solenoid often delivers higher starting torque compared to other linear solenoid. This is also ideal for automated systems since it has high shock and vibration resistance. For its application, rotary solenoids was used for switches and robotics.
Good day everyone. Today we're talking about the magnetic field inside a solenoid. Solenoid is a long coil of wire with many turns wound closely together in the shape of a cylinder. When an electric current flows through the wire, it produces a magnetic field that is very similar to the field of a wire magnet. This magnetic field has both a north and a south pole, and the field lines inside the solenoid are straight, parallel, and evenly spaced, which means the field is uniform inside. Now, to determine the strength of this magnetic field, we use the Ampere's law. Ampere's law states that the total magnetic field around the closed path is equal to the product of the permeability of free space and the current enclosed by that path. So the equation is written below. In the case of a solenoid, the magnetic field inside is uniform and runs parallel to its axis. Suppose the solenoid has a turns per unit length and carries a current. The total current enclosed by the path is then the N times the I times the L, where L is the length of the solenoid. Substitutes it into Ampere's law. We get beta times L is equals to mu O times N times I times L. After cancelling L from both sides, the equations become beta is equals to mu O times N times I. where B represents the magnetic field inside the solenoid. Mu is the permeability of free space equal to 4 pi times 10 raised to negative 7. N is the number of turns per unit length and I is the current flowing through the solenoid. This means the magnetic field inside the solenoid depends on two main factors, the number of turns per unit length and the current flowing through it. The greater these values, the stronger the magnetic field becomes. Now let's discuss the long solenoid. Long solenoid is one whose length is much greater than its radius. It's made up of a wire wound in the form of a helix where each turn lines very close to the next. Each turn can be treated as a small circular loop, and the total magnetic field inside is the vector sum of the fields produced by all these loops. To prevent the turns from touching each other, enameled wires are used for winding. This coating insulates each turn. For a long solenoid, the magnetic field inside is given by the same expression. Beta is equals to mu O times N times I. However, the magnetic field at a point of one end of a long solenoid is only half of the field inside, and it is given by beta is equals to mu O times N times I all over 2. In summary, a solenoid behaves like an electromagnet, producing a magnetic field that is strong, uniform, and controllable. The field strength depends on how tightly the coil is wound and how much current flows through it. A long solenoid simply provides a more ideal, uniform field because its length is much greater than its radius. That's how Ampere's law helps us understand the calculation of the magnetic field inside the solenoids and long solenoids. Thank you.
Next, what is toroid? A toroid is defined as a type of solenoid which is bent to join its two ends. It creates a helical shaped loop. It also has a large number of windings to operate properly. Its shape is almost similar to that of a donut as shown in the figure, and also has a hole in its center. It is generally made from a ferromagnetic core, and due to this, it is a soft magnet as well as operated according to the need. Additionally, the direction of its magnetic field is along its cross section, and due to this, its magnetic field is more stable. Its core can also increase its effectiveness. It also prevents a considerable amount of flux leakage outside of it because of its symmetry, and due to this, it has a very low electromagnetic interference.
Now, let's talk about the toroid and the magnetic field inside it. A toroid is a circular coil shaped like a ring. It's formed by bending a solenoid into a closed loop. When an electric current flows through the coil, it produces a magnetic field that is confined within the ring, meaning the field stays mostly inside the toroid and is very weak outside. To find the magnetic field inside a toroid, we use Ampere's law, which states that the total magnetic field around the closed path is equal to the product of the permeability of free space and the enclosed current. Mathematically, this is written as the equation below. Inside the toroid, the magnetic field lines form concentric circles, and the field has the same strength at very point along a circular path of radius, which is denoted as R. Using Ampere's law, we get beta times the quantity of 2 pi r equals to the mu O times N times I, where N is the total number of turns in the toroid. Then let's rearrange the equation. It gives us beta is equals to mu O times N times I all over 2 pi r. So beta represents magnetic field inside the toroid. Mu O is the permeability of free space, N is the total number of turns, I is the current through the wire, and R is the mean radius of the toroid. In conclusion, the magnetic field inside the toroid depends on the current and the number of turns and the radius. What makes the toroid special is that its magnetic field is strong, circular, and completely confined within the ring, making it very efficient for use in devices like transformers and inductors. That's all. Thank you.
Working principle of solenoid and toroid. Both solenoids, which has cylindrical coils, and toroids, which has ring-shaped coils, utilize electromagnetism generating a magnetic field when an electric current passes through the coil. Solenoid produces a nearly uniform magnetic field parallel to its axis, whose strength and directions are easily controlled by adjusting the current. For further explanation, a solenoid is a long coil of wire wound in the shape of a cylinder. When an electric current passes through it, it creates a magnetic field along the length of the coil. The field inside the solenoid is almost uniform and strong, while the field outside is weak and spreads cut. The magnetic field lines run from one end of the solenoid to the other, similar to the north pole and south pole of a bar magnet. Adding a soft iron core inside the solenoid makes the magnetic field stronger. On the other hand, toroid, its ring geometry causes the magnetic field lines to be entirely contained within the core in closed loops. The closed paths makes the toroid highly efficient and focused, minimizing external interference. For further explanation, a toroid is a wire wound in the shape of a circular ring. When current flows through the toroid, it creates a magnetic field that is completely confined inside the ring. The field lines form closed circles inside the core, and there is almost no magnetic fields outside the toroid. This makes toroids very efficient for application where a confined magnetic field is needed. Construction of solenoid and toroid. Both the solenoid and the toroid are electromagnets that generate a magnetic field when an electric current passes through their coiled wire. Solenoid. The field is used to exert a force, typically on an internal core or plunger, to create a motion. Solenoids are cylindrical in shape, where the number of turns of the conducting wire has circular loops. The current carrying coil is connected to the current, and a magnetic field is generated inside the coil due to the current flow. Due to the current passing through the coil, magnetic field is generated around it, and the magnetic field is applied to the core, and the plunger inside the coil moves. While toroid, its closed circular geometry completely confines the magnetic field within the core. It minimizes leakage, resulting in a highly efficient component where the inductance is generated and contained internally. Solenoid and toroid have the same construction. It's just that for a toroid, it has a circular ring-type structure which has several turns and forms a circular loop. The current is passed through the coil and a magnetic field is generated in the coil. Magnetic field does not leak here as inductance is generated inside the coil.
For the similarities, both toroid and solenoid has the same working principle. They both obey the principle of electromagnetism. Since the magnetic field is created generally due to the motion of the charged particle and vice versa, and it has the interaction between the electric and the magnetic fields. Also, both toroid and solenoid behave as an electromagnet, although they differ in shape and how their magnetic fields are distributed. For solenoid, a strong and nearly uniform magnetic field was generated inside the coil, and there is a weak field outside of it. On the other hand, the creation of the magnetic field of toroid was confined within its core. And lastly, both toroid and solenoid has the same and uniform magnetic field inside of them. However, solenoid has a linear field while toroid has a contained field with minimal leakages. Now, let's talk about the differences of toroid and solenoid according to its appearance, magnetic field, symmetry, and its stability. For its appearance, toroid is circular, having a large radius while having a short axial length, while solenoid has a small radius having a long axial length. Also, according to their magnetic field, a toroid has a uniform magnetic field created inside of it, which is confined entirely within its core. However, solenoid has a magnetic field created outside and a uniform magnetic field inside that extends outside of the core. Also, toroid has symmetry, which means its magnetic field is uniformly distributed along its circular path, and remains constant at any point equidistant from the center, while the solenoid do not have this symmetry. While for its stability, toroid is more stable magnetic field than solenoid, and solenoid, on the other hand, has less stable magnetic field compared to toroid.
Lastly, the different applications of solenoid and toroid. Solenoids are used on electric locking systems, dialysis machines, and other medical equipments, industrial devices like rotating, pinching, etc., transducer gadgets, electric motors, and electric generators. On the other hand, toroids are used on stators in DC motors, electric circuits, amplifier in computers, radios, televisions, and laptops, modern medical devices, electric power supply circuits, musical instruments, telecommunication devices, and inverters. So that's all for our discussion about solenoid and toroid. Good day and thank you.